Welcome back. This is an example of proving that limits exist. In general, we're going to prove that the limit as x approaches a of a function f of x equals L. And according to the definition of limit, we need to show the following. We need to show if the absolute value of x minus a is strictly between 0 and delta, that implies the absolute value of f of x minus L is less than some epsilon. Or maybe even more specifically, we need to show if some epsilon greater than 0 is given, we can find a delta greater than 0 such that the following implication holds. Alright, let's just work through an example. Let me move this page. We're going to look at a linear example. We're going to prove that the limit as x approaches 3 of 2x minus 5 equals 1. Okay. Step 1. We need to find a delta, and it'll be in terms of epsilon, and it'll be positive, such that if we assume that absolute value of x minus 3 is between 0 and delta, that will imply f of x minus L is less than the given epsilon. Okay, we're going to be given an arbitrary epsilon. And if we look at our example here, a is 3, so I wrote down x minus 3 in the absolute value. Our function is 2x minus 5, so that's the role of f of x, and the 1 is the limit. And so you might, if you want to, you can stop the video and compare what I just wrote with the definition of limit. So that's what we need to find. Well, let's do that. So how do we go about finding that delta? We start by looking at f of x minus L, which is our 2x minus 5 minus 1. We simplify the expression inside the absolute value. And we're trying to find a connection between this simplified form, 2x minus 3, and this expression in that estimates the size of delta. Well, I can see a pretty clear connection between x minus 3 and 2x minus 6. This expression down here is twice as big as that difference. So that leads me to factoring the absolute value, factoring out the 2. An absolute value of 2 is just 2. And now I have a product that includes the expression we have control of. Okay, so this tells me that it is reasonable to define delta as epsilon over 2. Okay, let's see why this was going to work. Step 2. This is our proof. Okay, assume epsilon is greater than 0, and that's been given. It's some small number. We don't know what it is, but it has to be arbitrary. We will define delta to be epsilon over 2. Whatever epsilon is, delta will be half that. Okay. We define delta to be epsilon over 2. Now, if we also assume that the absolute value of x minus 3 is between 0 and delta, then we can show the following. We can look at the difference, f of x minus L, and we know what that is. That's 2x minus 5 minus 1, which simplifies to 2x minus 6. We've already seen that we can factor out the 2, and so the difference f of x minus L can be written in terms of the difference x minus a. Now we look back. We've already assumed the difference x minus 3 is less than delta. So that implies 2 times x minus 3 absolute value is less than 2 times delta? Well, delta has been defined as epsilon over 2. So 2 times delta would be 2 times epsilon over 2, which simplifies to epsilon. And by the transitive property of inequalities, excuse me, I've lost hold of my pen. By the transitive property of inequalities, we have just shown that f of x minus L is actually less than epsilon. End of proof. Thank you very much.